I'm just going to go through a few high points in chapter 1. There's only going to be 4 or 5 ideas I mention here, most of which you've probably seen before, but I'm just going to officially do it to say that we've done it. So the first thing we want to discuss is the division algorithm, which is theorem 1.1. Okay, and it says let a and b be integers with b greater than 0. Then there exist unique integers q and r such that a is bq plus r, and there's a restriction on r can be 0, but it's between 0 and b. It can be 0, but it's strictly less than b. Now, they're using q here for quotient and r here for remainder, so that will help you remember those. So a and b are the numbers you're starting with. Okay, so let's look at an example here. 2 examples. Suppose a were 19 and b were 3. Okay, so if a is 19 and b is 3, I'm interested in what are the unique integers q and r that satisfy this. So 19 is going to be 3 times something plus something else. Now there's a restriction on the number here. Remember, this number can be anything, the q, but what's r? R has to be at least 0, and it's strictly less than the 3. So think of it this way. It's 19, you're dividing by 3. And so the number here is the quotient, and that's the remainder. And so it's going to be 6 and 1, isn't it? 18 plus 1 is 19. And notice my r here is bigger than 0, but strictly less than b. Okay, that's old news. Let's do another one. Suppose, on the other hand, a were negative 37 and b were 5. Okay, so we want to do the same thing. Let's find the q and the r. Negative 37. Notice it doesn't say a. It says b has to be positive here, but a doesn't have to be. Negative 37. So it's 5 times something plus something else. Now you have to be careful. Okay, I'm doing this one with a negative just to show you. You can't just say, oh, 19 divided by 3 is 6 plus a remainder of 1. Okay, it's not so simple when you have a negative number here. Because if I say, oh, 37 divided by 5, well, that'd be 7, right? Plus what? Well, if I put if I say negative 7, right, negative 7, that'd be negative 35. What would have to go here to make this true? I'd have to have a negative 2, and r has to be positive, so that doesn't work. So you have to be careful with the negatives, right? If I have to put a 0 or a positive number in for r, right, that means I have to, negative 7 is not good enough. It wouldn't be, it's only negative 35. You have to go over the negative 37. So if I say negative 8 here, notice that's negative 40, and now I add something positive to it to get negative 37. That's negative, no it didn't. Try that again. Positive 8. Okay, so here the q is negative 8, so you can't just say 37 over 5. That's not going to get you your 8 like we did up there. So if your a is positive, if a and b are both positive, it's no problem finding the q and r. You just divide the quotient and the usual remainder. But if your a is negative, you have to watch the q. Just check. Remember, r has to be non-negative. And notice 3 is strictly less than b. Okay, so that's the division algorithm. Okay, now we have a definition, which you learned in Math 223. Let a and b be integers with b not equal to 0. Then b divides a if a equals bc or some c in z. Remember, capital Z here being integers. Alright, and so why not b equal to 0? Because if b is allowed to be 0, then 0 times c would be 0. A has to be 0. So you put yourself in a box, right? If b is 0, a has to be 0. So it's not very interesting. Okay, so remember there are other ways of writing the same definition. You can say b divides a, b is a divisor of a, b is a factor of a, or a is a multiple of b. So all those are saying the same thing. So again, it was the same words that you used in Math 223. And remember the notation, right? B divides a, you write b divides a, right, with a vertical line. Right, so that's b divides a. No order matters here, right? B divides a and a divides b are not the same thing. Or b doesn't divide a. It's the vertical line with a little hash through it. So b divides a, b doesn't divide a. Okay. Now be careful. Right. B divides a means a can be written as b times c for some integer c. This means this. B divides a is not a number. I'll have students write all the time, 4 divides 12 equals 3. That makes no sense at all. This is not a number. It is an idea, right? 4 divides 12 is not the C, okay? Don't write 4 divides 12 equals a number. That doesn't make any sense. 4 divides 12 means 12 is 4 times something for some integer. Oh, it turns out it's 3, okay? So please don't write that. That doesn't make any sense. Okay. So, fine. Notation. So I'm kind of jumping ahead here. Other notation is the GCD of two integers a and b is denoted parentheses ab. So I know it looks like an ordered pair, but you have to take this out of context. So if you have two integers in an ordered pair like this, and you understand we're talking about, you know, this and not ordered pairs, this is the greatest common divisor of both of them, the GCD. Okay, so definition related to this, right? If the greatest common divisor of a and b is 1, we say a and b are relatively prime to each other. Okay, so if the greatest common divisor of two integers is 1, we say that those numbers are relatively prime. So for example, 16 and 25 are relatively prime. Notice 16 is not a prime number and 25 is not a prime number, but they are relatively prime because the greatest common divisor of both of the two numbers is 1. Okay. Okay, so now I'm going to shift ahead to a theorem. Theorem 1, 2 here says, let a and b be integers, not both 0. So one of them could be 0, but not both. And let d be the greatest common divisor of the two. Then there exists, not necessarily unique, okay, so there could be more than one way to do this, integers u and v such that d is au plus dv. Okay, so in the terms of linear algebra notation, you can write the greatest common divisor of two integers as a linear combination of the integers. That's what we have here. So that's just a fact that we're probably going to wind up using in the future, here and there, which is why I'm mentioning it now, just so we can say we've seen it. So let's look at an example here. Suppose a is 30 and b is 42. So those are my two they're both non-zero here, integers I'm starting with. Now what's d here? What's the greatest common divisor of 30 and 42? looks like it's 6, isn't it? Okay, so according to this theorem, I can write 6 as 30 times something plus 42 times something. Okay, so the theorem says we can find integers that make this equation true, and let me see, if I put a 3 here and a negative 2 here, that's 90 minus 84, which is 6, yeah, so fine. Notice the theorem doesn't say how to find it. I'm sure there are algorithms to do that, but I think when we use this later, we don't need to necessarily know what they are. We just need to know that the u and the v exist. Okay, then lastly here, just one of the theorems to mention, which again I know you know. This is theorem 1.8, which is called the fundamental theorem of arithmetic. Those in history and math last semester have seen this. It says every integer in greater than or equal to 2 is a product of primes, and this factorization is unique. Now, what does that mean? Right. So you pick your favorite integer that's at least 2. You can write it as a product of prime numbers. Okay. So for example, if you pick 6, see, you can write 2 times 3, but I could write 3 times 2. Now, is this considered a different factorization, right? So that's the question. So, right. So when they say the factorization is unique, what they mean is there's 3 things here. So the list of primes are the same. So this list and this list are the same. The exponents on the primes are the same. There's 3 to the first, 3 to the first, 2 to the first, 2 to the first. Okay. So when they say the factorization is unique, that's what they mean. So order doesn't matter. Okay. Okay. So order doesn't matter. Okay. So for example, if we did another integer and you wrote 2 squared times 3 times 5 squared times 7, whatever integer that is. If I do the same factorization into a product of primes, I'll have to have the same numbers, I'll have to have the same exponents, right? I'm not gonna have a 2 on a 3, second power on the 3, it'll have to be on the 2 and the 5. So the only other way I could do it differently would be the order. Right? But we consider them the same factorization, because order doesn't matter. Okay? Okay, so that's sort of the material that we're gonna need in chapter 1 as we move forward.